The next principle is the principle of randomization. And the idea is we'd like to randomize event-related designs, and we'd like to randomize them individually for each participant, so we don't have the same order for everybody. In addition, if we can't randomize the order of events, we can use catch trials. And what that can help us do is decorrelate predictors in our design matrix. So as a very fundamental principle, making the causal inference that it's the experimental manipulations that I've done that are causing the change in brain activity I've observed requires randomization to avoid confounds. And even if I randomize the design in the same and use the same design for every person, there are systematic differences due to imperfect randomization and finite sequences of trials and length of scan that will cause confounds. And so I don't recommend using the same order of events for everybody. Another example is a case where we have temporal dependence. If trial type A always precedes trial type B right afterwards, then the brain may show spurious A versus B differences for several reasons. One is neural habituation. If I always have A and then B, and even if they otherwise would have produced the same neural activity, if the response to B is simply reduced because of neural habituation or fatigue, it'll look like it's lower in that experiment. Secondly, vascular elasticity, which is a kind of nonlinearity. So if A produces a response, the blood vessels dilate. When B happens, the blood vessels are already dilated, so they can't go further. And then C, psychological changes caused by order are quite common. So 3 confounds. Let's look at an example of such a design and what we might do about it. So this is a working memory design in which I'm asked to remember a series of words. So here I'm remembering the words, and what I'm interested in is how those words are maintained during a delay period where there's no stimuli presented. Finally, I'm given a series of probes that probe my memory. Now in this design, let's say I'm going to model the encoding period and the delay period in blue and red respectively. Well, encoding always precedes delay. It's not possible to randomize the order of those conditions. So what do I do? First, let's look at a bad idea. So here's the design where there's always dependency. And now I'm just using a standard GLM, and as you'll notice, they're not perfectly correlated. And you can look at the correlation and you say, okay, maybe it's okay. Correlation is only 0.45, right? So you can get a response. You can estimate the response for those 2 regressors, potentially. But this makes strong assumptions and strong reliance on the assumption that the HRF shape is exactly correct. This is not likely to be true in practice most of the time. And if it's not, I'll get a wrong answer without knowing it. I'm going to interpret encoding-related activity as delay-related and vice versa, simply because the hemodynamics aren't modeled correctly, and so I'm getting the wrong partitioning of variance. So here's a better design. And what I'd like to do is model the responses flexibly. So I'm allowing the HRF shape to vary using an FIR model. However, using this model reveals the fundamental problems with this kind of design. And the problems show up as correlations in the design matrix. So here, we have a fixed interstimulus interval, intertrial interval here of 20 seconds. So regressors for trial type A are correlated with themselves, shifted over in time. That's collinearity. And in addition, what's happening in what's estimated as linked to encoding, event A, is correlated with what's happening to B at earlier time points. So we got cross-correlation across the different regressors for A and for B. And the maximum correlation here is about 0.93, but that's just because of how we sampled the HRF. And in fact, there's really perfect dependence across the columns of A and B. And what that means is, take a time point sometime during the delay period. I can't tell whether that activity is related to the delay or related to what's happening at encoding, residual effects of that. Now let's look at a better design still. So this is a catch trial design. So what's happening here is, on half the trials, I've got encoding only, and I don't present the delay period. I say trial's over. And what that means is now the B event, red, follows the blue only on half the trials. Now when I build that FIR design matrix, I've got 2 good features. First of all, I've got jitter, variability in the onsets, and that reduces the correlations within trial type A shifted over. So that takes care of that problem. And secondly, these catch trials or partial trials reduce the correlations between trial type A and B, in this case when they're dependent in time. So now the maximum correlation in my fMRI model is only 0.47, so that's better. That might give me a good shot at estimating the activity related to encoding and delay. So the next principle is the principle of nonlinearity, or issues with nonlinearity. And the idea is we'd like to avoid nonlinear interactions among events by spacing them at least a few seconds, 3 or 4 seconds apart. And also avoid systematic differences in temporal grouping across different event types. You don't want a design where all the trial type A's are clustered together and all the trial type B's are very sparse, because differences in effects of nonlinearity will systematically confound the differences across trial types. So historically, the idea has been that the bold response is roughly linear when it's presented repeatedly in time. So if you have an event at time 1 and 2 seconds later and 2 seconds later, you get roughly the same response to each of those different events. However, the operative word here is roughly. So Mize and al. And Randy Buckner showed that if you present events of the same type 5 seconds apart, the response to the second event is 10% smaller. That's a nonlinear saturation effect that's due to a combination of neural and vascular factors. Either way, they're not things that we can account for when we do the GLM very easily. And now I'll show you some data from a study that we did some years back, and it's designed to analyze the linearity or nonlinearity in the response. So what we've got is a series of events, one flashing checkerboard, or flash, 2 checkerboards a second apart, or a series of 5 or 6 or 10 or 11 checkerboards, all 1 second apart. We'll look in the visual cortex where we know we should see responses. On the left here, you see the actual data from the series of 1, 2, 5, 6, 10, 11 sequences of flashes. So we can see we have really nice data, nice responses. On the right is what we predict from the linear model. And I've normalized them so that the response to one flashing checkerboard, one event, is the same. But the linear model predicts that the response to 2 checkerboards is about twice as high as 1. What actually happens is it's only 1.5 times as high. So that's a substantial nonlinear effect that we're not going to be able to account for easily in the GLM. This happened in part because these events were 1 second apart. If you space them out 3 or 4 seconds apart, this nonlinear effect will be much reduced, and your linear model will fit better. So that's the first line of defense, is just to avoid very rapid presentations. And having a good model of linearity can also help us to understand efficiency in a deeper way. So what we're seeing here is a plot of efficiency as a function of the interstimulus interval, how long between events on average for a random event-related design. 0 would mean, or close to 0, is presenting events very, very rapidly. And with a true linear time invariant system, then what happens is, as you present events very rapidly, the contrast efficiency goes up infinitely. So if I could present a trial type A once every millisecond, 1,000 times in a second, I would get 1,000 times the response. Compare that to B, and you have a huge efficiency. Obviously, the brain doesn't really work like that. So having a sensible model of nonlinearity is critical for understanding what's the optimal presentation rate. So now on the right here, what we're looking at is a more realistic model with a simple model of nonlinearity that won't let the response go up too high. And now what we see is something useful. What we see is if we're looking at a contrast, 1 minus 1, that's a task A versus B comparison, then the best design has an interstimulus interval of about a stimulus every 2 seconds or so, and no rest. If all I care about is comparing A versus B, I should fill my task with A's and B's. I don't need to jitter or have any rest, and that's optimal. Once I start including rest intervals, which creates jitter in the design, then the efficiency only goes down. The last principle is optimization. Optimize your design choices with specific study goals and constraints in mind. They could be psychological, neural, or statistical. In particular, we'll look at specifying a series of things. One is specify a set of contrasts that you care about. If it's an ANOVA design, 2x2 ANOVA, you might specify that you care about the main effects and the interaction. That's 3 contrasts. You can specify the relative importance of each contrast and think about which effects you really care about detecting. You can also think about the desired high-pass filter cutoff, how much noise do you want to remove, and so how much do you need to keep the design out of that noise range. And also you can think about the desired model that you like to run or use. So do you want to use a canonical HRF, or would you like to use an FIR model and try to estimate the shape of the response? So it depends on your goals. And now we'll just look at the first principle, which is thinking about which contrast you care about. So let's say we're doing a study with famous versus non-famous faces. That's trial type A and B. And what I really care about is the difference. All I care about is the difference, A versus B. In that case, what I told you a moment ago applies. The best design has no rest and pretty rapid presentations of events, a face every 2 seconds or so. But now let's consider that you also want to tell whether the fusiform face area is activated by faces on average. That's a different contrast. And that contrast is the average of the famous and non-famous faces against the implicit baseline, or rest. Now, in this case, the optimal design is different. Now the optimal design has 50% rest intervals. So there's still rapid trials, so you can still present a trial every couple of seconds, but half the trial should be faces and half should be rest, if you'd like to estimate the face versus rest difference as well. So if you care about both of those contrasts, you have to optimize for a hybrid of those two effects. And by the way, what exactly the peak ISI is here really depends on my nonlinearity model. So in practice, I might be a little bit less aggressive and not present events quite so fast together, right? I'm saying 2 seconds or so is pretty good. But I might push it out a little bit just to avoid nonlinearity in case the nonlinearity is not quite what I observed in my experiment. So now we've talked about 8 principles of fMRI design. We've talked about considerations of sample size and scan time. We've talked about how many conditions to include in your experiment and how to group the events in those conditions together and organize them. We've talked about temporal frequencies and the need to use designs with the right temporal frequencies, not too short and not too long. 18-second to 20-second blocks is optimal. We talked about the need for randomization in designs, and we've talked about what to do in some cases where you can't actually randomize the order of events. And we've talked about the effects and implications of nonlinearity and some principles underlying design optimization. So that's the end of this module. In the next module, we're going to continue our work on design optimization and talk about computer-aided design using a genetic algorithm and put some of these pieces together.